when we think of query behavior, um, we kind of like to think about um, we kind of like to think that it looks something like graph number one, meaning the more power I give the query, the more it's going to cost, but the more performant it's going to be. The truth is that queries behave in a kind of weird way. And the thing is that not only do different queries behave differently, but the same query can behave differently depending on where it is, meaning depending on the amount of power you give that query. So a specific query can behave like number two if you decide to move between a small warehouse and a medium warehouse, and it can behave like number three if you decide to move between a medium warehouse and a large warehouse. The thing is that when you look at a group of queries, the group of queries usually does behave like number one. But the individual query can behave like number two, number three, and number four. And the question is, when we look at optimizing a query, the question is, what information do we have in order to optimize that query? And how can we identify where it stands, like which one of these, like where it is, is it number two, number three, or number four? Because that will basically tell me, depending if I want to optimize that query for cost or for performance, it will tell me if I could give that query more power, if it's going to cost me more, if it's going to be more performant, or if I'm just going to pay more. And in some cases, I could actually give the query more power. It's going to run so much faster that it's actually going to cost me less. So I really want to understand where I am. So when we started building this algorithm for optimizing the warehouse for the queries for the workloads, we tried to understand what's the information that we can get from Snowflake that could hint where we are. So we looked at a couple of different KPIs that Snowflake provided to us, and I think the KPIs that we have here are the ones that correlate most strongly to the query to the way the queries behave, and they're going to be fundamental in terms of building the algorithm later on to make me understand how to right size the warehouse based on the query load. So warehouse size, of course, warehouse size tells me the number of compute cores that I have and the available memory I have. Query load percent basically tells me how busy the warehouse is, how well utilized the compute is. Byte scanned, I think, is the most important KPI, but also the most difficult to understand. Basically, what I want to do, I want to somehow map bytes scanned into memory usage. It's super hard, almost impossible to do it perfectly, but there are some things that we could do in order to understand generally how it's going to behave. And when I talk about query loads, I only need the general environment. I don't need the specifics. The reason byte scanned is super important, the reason that the mapping of byte scanned to memory is super important is because the most influential metric that influences query speed is how much memory and how much spillage it has. So when you think of a query that uses the compute that is memory heavy, basically you could think of a parameter that every time every amount of data that moves from compute to RAM, and then from RAM to SSD, and then from SSD to HDD, it's kind of like a multiple of times 3. So theoretically, if I could take a query from a query from HHD and move it to RAM, I could increase query speed by a multiple of 6. So when I try to map byte scan to memory, basically what I'm trying to predict is how the spillage will behave. If I'll be local, if I'll be remote, and so on. And then, of course, everything here then relates to query duration, because at the end, what we pay for is the query duration, the amount of time I'm actually processing.